right, I think we are live-ish. I'm afraid my internet is a little bit laggy today, so if things are looking bad and choppy, then let me know and I'll see if there's something I can do, but I'm not certain there's going to be. But I think it'll be okay. Okay enough. All right. What we're doing today on the screen here is stress and strain. So stress, we talked about, we're still axial, right? We're still, all the forces that were applied are axial, meaning that the external forces are along the longitudinal axis of whatever object we're dealing with. The new topic, kind of 2 or 3 new topics, is strain is one of these. And then the combination of stress and strain together is a topic we'll cover today. And then last time we also talked about the idea of ultimate strength. We talked about yield strength. I think those are the only 2 that we actually mentioned as far as strength goes. We'll cover how those are determined. How do you figure out what the ultimate strength is? How do you figure out what the yield strength is? And then a couple of other material properties that are going to be of interest later. They're just not quite there yet. Actually, one of them may be a little bit interesting today. So why don't we head off into, I think I want to do Solidworks first. Let's do that because I'd like to get Solidworks done. It's kind of a memory hog, and so I want to go ahead and close it down as soon as we can. So what I'm going to build in Solidworks is a tensile test specimen. Let's build it this way. Actually, no, let's not build it that way. Discard those changes. Let's do a revolution. That'll probably work better. All right. So what I want is, I want to it's waiting for Solidworks to respond. It kind of is. There we go. All right. Now that's not the line we want, but it took a while to wake up. All right, we'll build a axis here. We'll just make this a construction. This is what we'll revolve around. And then what we're going to build is called a tensile test specimen. I don't know if you've seen one before. Maybe if you've taken a materials class, you have seen one. But this is going to be our round tensile test specimen. I guess I didn't have to have that axis to rotate around because I have the line I just drew, but that's fine. Now these have particular dimensions. This is called, this length right here is the reduced section, and it's 2.5 inches long on a tensile test specimen. These are kind of arbitrary. These sections would be just threaded. We can make them 1 inch. That'll be fine. Let's put this one at 1 inch. The diameter, well, I guess I have the radius here, right? The radius of this is actually right. It should be, there's 2 different sizes. We're going to use the 1/2 inch size. Oh, but that means the radius is 0.25. This part doesn't matter so much. It's just, again, it's the threaded part. We'll make, let's make it, it doesn't matter. We'll make it at 0.5 just to have it there. And one other thing we need to do is we need a fillet on this corner and on this corner, and that fillet has a radius of 3/8 of an inch. Except it doesn't want to give me let me do a 3/8 inch radius. What if we do 1/4? Well, it should be, maybe it's 0.2. All right, that'll be good enough. And technically it's supposed to be 3/8 of an inch radius. Oh, you know why? It's because of this 1/2 inch. I'm probably supposed to make that a little bit larger. That's okay. What it creates is the gauge length would be this line, and I assume I'll have a little bit longer gauge length than you technically should have. The gauge length should be 2 inches. Let's go ahead and revolve this so we can see what it looks like. There we go. Sort of like that. And so this is our tensile test specimen. These ends here and here, they would be threaded to fit into your machine. They make other types of tensile test specimen, flat ones for different materials. This is kind of your typical round one for a ductile metal. You bolt it into a machine that's going to pull it apart. And this surface here is called the gauge region. And it's reduced in size, right? So it's should be where this thing is going to fail. You do load these to failure, so eventually this will snap in half. Let's do a little simulation and kind of show what this would look like if we were to put some stress on it. We'll do a static simulation. Now these do stretch over time, so it actually should be maybe a time sensitive simulation, but we'll do it this way. We do have to add a material, which last time we tried adding a material took quite a long time to get the material to pop up, but we need to do that again. So the point of these, while we're waiting for it to pop up and tell us that we can add a material, the point of these things is that you may have an unknown material that you're working with, and or even if it's known, you may want to verify that it's to some standard. And you want to know some certain material properties of this sample, and this sample represents, you know, maybe all the metal pieces in a machine you're trying to build or whatever. And we're going to apply a force. Well, technically we are going to apply a force, but technically we're actually applying a displacement. So we're actually going to pull apart from the top and bottom. So we're going to pull the top away from the bottom of this tensile test specimen. While we're doing that, we're going to measure the force that's being applied, how much force are we having to pull with, and the displacement, how far have we moved the top of the sample from the bottom of the sample. So, you know, how much is it stretched? And we're going to simultaneously record both of those pieces of data over and over multiple times a second, and we'll be able to plot the result of force versus displacement on an XY, you know, type of plot. Here's our materials. All right, we're just going to use this alloy steel, apply that to everything, and now this is some generic steel. We're going to let's fix the bottom here. This will simulate it's bolted into the bottom of our tensile test machine. Probably let's go ahead and fix the bottom also, just to have that. And let's apply an external load force. I don't know. Let's see. Can I apply a displacement? Hold on. I've never. No, the way I've got it set up with the static load, I have to apply a force. But again, well, there's a prescribed displacement. I could do that. Let's just do a force and it'll be fine. Because we're not trying to get any actual data off of this. We're just trying to simulate. That is not the direction. I don't want to press on this. I want to pull upwards. So let's select a direction. Let's see. I may have to find, oh, here we go. Force is going to be in the English system will be fine. And I don't, per item. Actually, I could just apply it to here, couldn't I? I wanted to unselect that, but I don't think I can. There we go. All right, I want a selected direction. This won't be quite right if I apply it here, but it will be okay. Let's apply it on that one. And this is a 1/2 inch diameter piece of steel, so it's going to take a lot of force to pull it apart. Let's say there's 20,000 pounds on this. And it's not showing me which direction. I think that's the way I want it to go. Oh. Oh, do I have to apply it to a edge? Oh, I wanted to apply it on this face. Why is it not letting me? Oh. Because this was the direction face. I was not applying it to a force. Let's see if I can. There we go. I have to figure out which one of the selections will actually apply it the way I want it to. Now we've got it set up. All right, so we're pulling up 20,000 pounds. We're affixed to our machine down here. So in the machine that we actually would put these in, they're both screwed in, and the crosshead that's on the top would actually lift up. Okay, had to check my stream. So it looks like it says an excellent connection right now, so maybe we're actually streaming okay. So we're pulling up. Let's do a mesh and run. Just take all the defaults, just so we can kind of see what will happen. And there is our tensile test specimen. Now, I kind of want to exaggerate this plot so that we might, I don't know if it'll be able to show us what's going to happen in the center down here, but let's try and see. Oh wait, it was over there. It's currently at a 48 times scale. Let's make it a 2,000 times scale, maybe. See if that will. All right, that's a bit much. That one's a little bit much. Let's reduce that slightly. I wasn't sure, but clearly that's too much. So not 2,000. Let's go with 200. All right, you can begin to see here. So what happens with these tensile test specimens, you can kind of see where the original was. Again, this is 200 times scale, but in real life, these do stretch, and you can physically see them stretch. What will also happen, that's not really, demonstrated very well in our simulation here, is that at some point, not necessarily in the very center, but some point in this gauge region, remember the 2-inch gauge region, somewhere in there, a little neck will begin to form. So it will reduce down even further. This simulation package in Solidworks is not going to really show that very well. I'm not even sure I could make Solidworks do that. I would need something maybe a little bit more sophisticated on the solver. I haven't actually tried that to get it to reduce down in this region in the center part. So it reduces and creates what's called a neck. So it's a thinner part somewhere in that gauge region. And so you do this, and you record the data. You record the force and displacement, force and displacement, and you plot it. And the plot that I'm going to exaggerate the plot. Let's close down SolidWorks so that we can get some of our memory back. We don't need to save that. And let's draw what this plot is going to look like. And again, I'm going to exaggerate this plot because oh, that's MathCAD. I can't draw on MathCAD. There we go. Get our ruler out. And let's draw a x-axis, something like this. Remember, on the x-axis, we're going to have displacement. I'll call that delta. So the way these machines work is The top part is affixed to a movable structure. Maybe there's a hydraulic cylinder or there's some power screws that lift the top crosshead, and you measure that displacement. At the same time that you're doing that, you are measuring the force, we'll call that F, and this force is measured by a load cell. Load cell is a calibrated piece of metal with some instrumentation on it, usually a strain gauge or multiple strain gauges. And those strain gauges, I know we don't know what the word strain necessarily means yet, but we will get to that soon. Those strain gauges are capable, the strain gauges combined with the load cell, so the strain gauges are part of the load cell. The load cell is capable of telling you how much force is applied to the load cell, and the load cell is connected between the crosshead of the machine and your sample. And so it knows how much force is being applied to this machine, or to this sample. And the plot that you'll get, it's going to look similar to this. There's going to be a straight, and so we're assuming that we are testing a ductile metal. So ductile means that it does have some ability to stretch before just fracturing. The opposite of ductile would be brittle. So brittle materials would be like glass. You don't really stretch glass very much before it shatters. But metals, they can have a little bit of stretch before they actually fracture. So the first thing that's going to happen is there will be a linear portion. So some sort of straight line. I'm going to exaggerate the slope of this. So normally this is going to be much steeper, but I need some room to write things on our graph. So this is our linear region. Sometimes this is called the elastic region. And what's going on here is the atomic bonds holding all the molecules together are stretching out. So they're not really moving any molecules around in the crystalline structure of the sample, but the atomic bonds are starting to stretch out. And so that's more or less a linear process. And then at some point, it becomes nonlinear, and it looks sort of like this. And this is called the plastic region. If the other one was elastic, this is plastic region. Obviously, it's nonlinear. And here, we have the not just atomic bonds stretching. Now you're actually moving molecules around. So they're moving around on those slip planes. If you remember any of that kind of terminology from your materials class, these molecules are moving around. The thing that's different here, plastic versus elastic. Elastic, you think of an elastic band, like a rubber band. You stretch it out, and as long as you didn't break it, then you let go of it and it goes back to its original shape. Same thing with the metal. You've elastically stretched the atomic bonds, but as soon as you remove the force, it goes back to its original shape. Plastic, you have gone beyond just stretching bonds, and now you're moving molecules around. When you let go of the sample, it will not go back to its original shape. It'll be somewhere between where you stretched it to and where it started. It'll have some rebound, but not completely back to its original shape. And so that's why it's plastic. And then once you get to this part, that's where that necking occurs. So you're really moving stuff around now. The necking that I'm talking about is with our little sample. Remember, our sample looked something like this. And the neck would be a reduced section somewhere in here. That's the neck. And so that's where you've really started to stretch it. A lot of times, you know, unless you've seen one of these tensile test experiments, then maybe you don't have a good vision for what that neck looks like. But a lot of times what I do, it's not the exact same thing, but mentally imagine something like taffy or some material that you have seen stretch. And in this part of the experiment, it kind of looks like that, where there's going to be some section. Now it's somewhere in the gauge region, and it's going to be, for whatever reason, it's the weakest link, and it's going to be the place where this necking begins. And once that's established, it only gets weaker, because this neck creates a smaller cross section than anywhere else. Smaller cross section there. Remember our idea of stress from last time. Stress was force over area. If this area gets smaller, then the same amount of force will create a higher stress, which will make it stretch even more, which makes the area even smaller, which makes it even higher stress under the same load, and it's a cycle to failure at that point. And so what does happen in our graph here is it goes down and breaks. Now, it could be, there's two different ways, at least two major ways to run this experiment. One of them is to do what I described earlier. You measure the force and you measure the displacement and you plot them like we've plotted here. The other one adds in a third variable, where you actually go in and measure this changing area. So you measure that, that area got smaller and smaller and smaller, and instead of plotting force versus displacement, you will plot stress versus this strain thing that we'll talk about later. And that stress value can be accounted for by the changing area. So you can put new values of area in your stress equation over and over, and that plot will look, like this. It'll keep going up because it's taking into account that, or it'll stay horizontal. It won't dip down anyway. It's taking into account the fact that you've got a smaller and smaller area. And the difference in these two, this one's called engineering. Whoops, there's two E's, aren't there? Engineering stress strain. And this one is called true stress strain plot. Wow, if I could spell them the right order, that would help. True stress strain. Now, right now, I don't have stress and strain plotted. I have force versus this delta displacement. In order to create stress, if you have force, you divide it by area, and force over area is sigma, so that's your stress. That's how you calculate stress, axial stress. And so to convert all the y-axis values into stress, you divide by the area. And if you're doing engineering stress strain, you divide by original area. In our little sample, we made that diameter 1/2 inch, so you would divide it by pi 1/2 inch squared over 4, and that would give you, divide the force by that, that would give you the stress. And it's stress strain. So the x-axis is going to be strain. So we haven't really talked about strain yet, but it's a very simple concept. And let's write it here. Strain has a new variable, this epsilon, and it equals a change in length divided by the original length of the thing. So it's really easy to deal with. Notice if I'm dividing length by length, I don't really have units. Inches divided by inches they cancel out. So it won't have units of anything like length or meters or anything like that. It will be percent or just strain. So it doesn't have a letter after it signifying some kind of units. It might have a percent sign saying percent strain. Otherwise, it's just strain. So this change in length is delta. That's what I have measured from my machine. I measured how far did the crosshead move during this experiment, and that's the change in length. The original length is not this length, because part of this, it's bolted inside the machine, and it's a larger diameter. So that's not the length that we're talking about. The length is this. This is original length. This is also called the gauge length. So it's the reduced section of the, well now, I've shown it with the neck here. So it's the original length before you start stretching it, right? So it's the gauge length. So original length, in this particular case, we might call it gauge length. Ran out of room on my screen. So I'm going to call it L naught. Delta specifically will be the final length minus the original length. Because, you could stretch something, or you could also have strain from compression, and that way you would have a negative strain. So you would need the final length to be shorter than the original length, and you'd end up with a negative sign in the numerator. So it could be that it's negative. Most of the time it's going to be a positive strain, but you could possibly have a negative strain if you compress something. All right, so to get our strain over here, all I have to do is divide by the original length, gauge length. In our samples, the gauge length is specified to be 2 inches for round samples. No, it does not include the bevel. So there was a question, does the gauge length include the bevel? No. So there's called the reduced length. That includes the bevel, or the fillet. And the gauge length is between the top fillet and bottom fillet. So it's just the cylindrical part of it, not the filleted part. That's a good question. So it's the reduced length is everything outside the threads, more or less, where the fillet begins. And the gauge length, the one that we're interested in calculating our equation here, is the between the fillets. So it doesn't include the fillet. That also tells me that y'all are at least able to see this thing, so that's good. I'm having to run off of a hotspot, so I don't know how stable that'll be. We'll see. So far, I guess it's okay. So if I divide that displacement from the machine by that original 2-inch gauge length, then I have created the equation for strain, and now I have a stress strain plot. So it would still look the same. The magnitudes of the numbers would change. Instead of force on the y-axis in pounds, now I have stress in KSI or PSI. And instead of actually on the x-axis, instead of inches, now I have no units, but I have this idea of strain. So I might have it presented as percent strain, or I might just have it as strain. Once you get this plot, now there are several material properties that we can obtain from a plot. Now, you would do multiple plots and kind of average out samples instead of just one sample. You would do this multiple times. Let's assume that this is our average plot. Again, recognizing that what I drew for our linear region probably is going to be much steeper than what I've drawn it, but I need a little bit of room to write stuff, so I made it not as steep as they normally are. Also, sometimes there's a little hump in here, and that's okay. We're kind of averaging that out and not dealing with it. So if you look at one of these in the real world, it might look or it will look slightly differently than what I've idealized here, but all the main features will still be visible. So let's do the easiest one first, at least the one that I think is the easiest, the peak. So this peak, that is ultimate strength. And we call that sigma U a lot of times. And so that's the ultimate strength. And it's just wherever the peak is. And you can kind of see now why last time I mentioned that you might not want to compare everything to ultimate strength. That's what we did. I think in the bearing example we did yield strength. But the ultimate strength includes some of this permanent deformation, permanent change in size or shape or geometry, from this part. And so you might not want to deal with ultimate strength in your designs because you probably don't want things to change shape in your machines you're working on or your buildings that you're designing. So that brings us to another one right here. This one, I'm going to call this the proportional limit. Let me get where I can write that. Proportional limit. This one is not quite any number that you're going to use. What it is it's where do you think, where the viewer of this graph, where do you think it is no longer linear? And so some people might say, well, it's no longer linear right here. Somebody else might drop it down somewhere a little below that. So there's a little bit of ambiguity where the proportional limit is. And that's no good. We don't like ambiguity when we're trying to design something. So what instead we do is we say, I'm okay with some amount of strain in my design, but it's a really tiny amount of strain. So I'm going to take 0.2% strain. And I'm going to say that I'm okay if my design has 0.2% strain, change in size of objects. And what I'm going to do is I'm going to draw a line from 0.2% strain parallel to the linear region. Let me see if I can get my, I'm just going to do it by hand. So parallel to this line, and it's going to intersect right there. And I'm going to say that this, so proportional limit's the lower one right here. This is the 0.2% offset yield strength. And that would be sigma y, is how we'll usually write that one, is with a y for yield. So the 0.2% offset is because I went down to 0.2% strain, offset the graph by that amount, and re-intersected the graph to figure out what my yield strength is. So that might take a little bit of explanation on why that's what we do, and this might help. So when you load up the object, this test specimen in this case, you know, it's going to travel up the graph, and then it's going to, as long as we don't fracture it, then in this case I have gone past the yield strength. So it does have some amount of permanent change in its shape. When I remove the force, if I'm at this point up at the top and I remove the force, it travels back parallel, whoops, lost my, parallel to that original linear region. So like this. So I'm going this direction. And now I have some amount, I don't know what that amount is. If that's 0.2, then this is, I don't know, or maybe it's more than I don't know, 1.2. I have 1.2% of permanent change in the geometry. If I don't exceed the yield strength, and I just go up here, when I let go of the force, it just comes right back straight down to no strain. So it doesn't permanently deform because I've only been in the elastic region. I haven't entered the plastic region where the permanent deformation occurs. Most of the time, that's where you want to stay. You want to stay in that elastic or linear region because that's where you're not going to induce any sort of permanent change in geometry. And that's generally bad. Sometimes you do that on purpose. Sometimes you intentionally move things past their yield point because now, look at the yellow line. The next time I load this piece, it's going to go from here up, and it doesn't change shape until a much higher point now. It doesn't. It has a new plastic region, a much higher plastic region. So sometimes you intentionally make things stronger by stretching them, deforming them, entering their plastic region, letting go so you don't fracture them, and then the next time you load them, they have a higher yield strength. So sometimes you do that on purpose, but that's usually not part of your machine. That's before you do that. I guess a specific example might be bolts. Sometimes you do yield bolts so that they work harden a little bit. All right. What else can we find? Oh, a very important thing that we can find on here. Like I was saying, most of the time you want to stay in this linear elastic region where you aren't inducing any kind of permanent change. So it has a feature that we're interested in, and it's the slope of this line. So let's see, we're going to write this. The slope is equal to what's called the modulus of elasticity. And we give it a variable capital E. And so that is important because it lets us write a linear equation relating stress to strain for our material. So if I only operate in the linear region, the straight line region, then sigma equals the slope of that line times the x-axis. So this is just y equals mx plus b. The y-intercept is 0, so plus 0, unless I've somehow moved it around. But you usually don't have a y-intercept on here. If you do like the yellow line where you move the point, you just move the origin back over to now it's at 1.2%, and you make that your new zero strain. Once you've let go of it, it's not strained anymore. It's not straining anymore. It's permanently strained. It's that size now. And the next time you load it, you can load it to a new strain level. This equation has a name, Hooke's law. Sometimes you hear Hooke's law and it's related to springs. How much force does it take to stretch a spring a certain amount? It's the same thing. Basically, we just have a really stiff spring here that is our tensile test specimen. Here, if I drop this down, this point is the strain at fracture. You don't lose that too much, or you don't use that too much, but that's what it's called. If you integrate the area under this curve, that's called toughness. I think those are our primary. Oh, this point, I kind of don't want to draw it over here, but this point is fracture strength. We'll just call it fracture. Again, you don't really want to operate over there because it's the failure point. Really, the failure point is up here. Once you get past or even to the ultimate strength, it's all down. It's literally downhill. If you look at the graph from here, and it's going to fail unless you immediately remove the force. And even then, it's weakened to the point that you wouldn't ever want to use that piece again in your machine. All right. I think that probably is all of the information we need for where we're going to get these material properties. Now what we need to do is let's find a sample of these material properties. So if you have the textbook, then you have a selection of these. I guess I should show you what I'm looking at. If you have Moodle, then there is a reference materials folder. I think it's on the one called Introduction at the very top, and there are material properties.pdf. This is basically the material property charts from the textbook. Also, you can just search for material properties on many different websites and you will find them. Let's look at the ones from the book so that we can kind of get an idea of what's going on in there. There are 2 pages here. They have the same set of materials on the left-hand side of each of these tables. What they are is they're 2 sets of units. The page 704, this top page, is the US unit set, and page 705 is the metric unit set. Same everything else, but different units. So do be sure you're using the correct unit set. Also, If you were, maybe you're working a problem and why is that on there? I don't know. Maybe you're working a problem and it has metric units and you only have access to the US unit chart here. That's fine. You can convert them. But if you're working a problem related to the course, then you might have issues because they don't convert exactly from one, like 48 KSI for this wrought iron ultimate strength is not 330 megapascals. There's some rounding that happens in these tables. So if you're using these tables for a course problem, use the right one. In the real world, they're close enough that it's okay to convert from one to the other if you don't have the other one. But in textbook problems, it's probably going to give you some issues if you use the wrong chart and convert, just because of the conversion is not in these tables is not 100% decimal related accurate. So let's zoom in and look at our table headings here. So first you have materials, and there's a whole set of irons and steels, aluminums. There's even some wood and concrete down here. You have their density, specific weight. You use that occasionally if you need to calculate the how much something weighs based on its volume. Then you have what's called elastic strength and ultimate strength. I wonder if I can write on here. It says I can annotate, but I can't actually annotate. Well, that's okay. That's all right. Well, I'll just point to stuff. All right. Or I could copy it. Let's copy it and paste it into Word because it would make it a little easier to annotate. Let's see. I'm going to have to zoom out a little bit, though, to get enough stuff on there. Let's copy that. We'll get a couple of rows. And then we'll go back over here. All right. So now we have it here. So elastic strength and ultimate strength. So the elastic one, that might make sense because, we've got this elastic region that we talked about. And ultimate strength is related somehow to the ultimate region or the plastic region. And there's 3 columns under each of these. There is a tension column, a compression column, and a shear column under each of elastic and ultimate. So last time we were looking at the ultimate tensile strength, and we said it was 60,000 KSI for this made-up material that we use. If I look here, let's just say, all right, so here's a generic material, structural steel. So this is not, it's just kind of a generic all-purpose steel that we could use just as kind of a placeholder. And if I want the ultimate strength of it, this number right here is 66 KSI. That would be what I would use for the ultimate strength of this generic structural steel material. If it was in compression, in tension. This column is tension, right? If it's in compression, it is B. So B means I need to go back to the chart and see what B actually means. For ductile metals, this is reading off of the B footnote. For ductile metals, those with an appreciable ultimate elongation. I didn't really talk about the elongation, but that's just how much it stretches. It is customary to assume the properties in compression have the same value as those in tension. So basically, for most of the materials we're going to use that are steel, particularly the steels, some of the aluminums may not be this way, but for most of the steel materials, the tension and compression numbers are the same strength. If I wanted the shear, we did do a shear. We did a shear of a pin and shear of a plate with a hole in it, a tear out. Here, there's just nothing listed. There's no letter. There's just blank. This is where you use your failure theory. Which failure theory do you want to use to generate the number here. And there are several failure theories you can use. So you choose the failure theory. Whoops, E. Oh, wow, that's messy. You don't know any failure theories currently, probably, unless you are retaking this course for some reason. But they're later on, 2 or 3 classes from now, 2 classes from now, I guess, you'll learn about different failure theories, and at that point, you'll have reason to choose one over the other. We're going to use one called maximum shear strain, and what it does is it says take the tensile number, 66 KSI, tensile strength, and divide it by 2. And that's going to equal the shear strength. And so for us, our shear strength, if we use this failure theory, is going to be 33 KSI. If I want the yield shear strength, I take half of the tensile yield number, 36, and I'll have 18. So this elastic number, that's the yield strength. Elastic strength and yield strength are the same term. And this 36 would be right here. And this ultimate strength would be this number. There is no number for proportional limit. It's more just a location on the graph where you estimate it's no longer linear. So it doesn't really have a number because everybody might estimate it differently. Now we do have to make sure that this is the 0.2% offset. So let's check our table again. Let's see. There you go. This A footnote says elastic strength may be represented by proportional limit, which we're not going to do, yield point or yield strength at a specified offset, usually 0.2% for ductile metals. So it doesn't specifically say which one of these it's using. I'm going to assume this is the 0.2% offset yield strength. That one's more consistent, versus just kind of picking a point off of the graph where it looks like it has changed from linear to nonlinear. The 0.2%. Now there are other like there's a 0.5%. Maybe you're okay with 0.5% strain in your design. So there is a 0.5%, I think. And so there can be other locations of offset, but we're going to assume that this is a 0.2% offset yield strength. Endurance limit, we don't need that one yet. That will be for later on, not this course, later on in another course. This is cut off. This word was modulus of elasticity. So that is this guy, the modulus of elasticity, which is the slope of the line. It does have odd units in this chart, so be careful. The units are thousands of KSI, so thousands of PSI, so it's 10 to the 6 PSI. And then for this particular material, it would be 29 million PSI would be the modulus of elasticity. We have this one, same thing, but this is rigidity. We'll do that at the end of the quarter. Modulus of elasticity talks about stretching somehow, an axial stretch or maybe a flexural stretch, and rigidity is twisting. So we don't need it just yet. And then there is a coefficient of thermal expansion so that if this thing heats up or cools down, you can kind of calculate how much it changes size. We don't need that one just yet. Actually, I don't think we'll use it at all in this course. So this type of chart and data produces this type of table with values for your material properties. And you have 2 of these tables with all sorts of materials in the 2 different unit systems that we're going to be dealing with, the metric and the US unit system. We have both of those in here. You'll notice that some of them do list particular numbers for the shear strength, so they don't follow the same pattern as where you choose the failure theory. Some of them list values for compression separate from tension, so they're not as ductile as the typical steels are. In fact, these are all aluminums right here and magnesium. And so you do have to be careful with the chart, but it's pretty straightforward to use it. Most of the time, we're going to be using this tensile yield strength number because that's the one that most of the time you're going to design for. Now, you'll have problems like exam problems and homework problems that specifically have you go look at things that aren't that, but most of the time you're going to need the yield strength, the elastic yield strength in tension for whatever you're designing, because most steels, if you have that tension number, then you know the shear number because you're going to apply your failure theory, divide by 2 for us, or you're going to just know that the compression and tension are the same value for most ductile metals, so most steels. Stainless steel even is the same, but there is this heat treated steel that has a little bit different compression and tension. Okay, now let's see what we've got. All this way to calculate material properties. We have this idea of strain. We haven't done anything with strain. Let's work on strain a little bit. So there are, just like there were 2 types of axial stress, 2 major types. There was the normal stress and the shear stress. We have the same 2 types of strain. Let's write in black. So we have an axial strain, and a little bit on, once we finish talking about axial strain, we'll have a shear strain also. So axial strain, let's just say got some sort of rod here, and we are applying an axial force, and this force happens to be a tensile force. It's pulling it apart. And let's put 1.5 kips. We haven't used kips at all, I don't think, so let's use some kips. This one also needs to be 1.5 kips, or else our piece is moving. It's either moving left or right, depending on which one of those forces is larger. Axial strain does care how much force is applied to this thing, but it's really the change in length, right? So right now I'm going to have a hard time calculating axial strain, but let's add some more information. Let's give this a I don't know, we got 1,500 pounds on it. Let's give it a 1/4 inch diameter. And let's give it a particular material now. Let's just use that generic structural steel. I doubt if you were to like go try and buy structural steel, that's probably not a thing. So most steel has a name associated with it. You know, it tells how much carbon is in it, how if it's hot rolled or hardened. You know, that, or 18.8. You know, if it's a stainless type thing, or a 4340. You know, it has a name. Structural steel is just this generic placeholder that when we don't need that level of precision, it's just going to be kind of a generic one. All right. So what I can do with this is I can calculate the stress. We did that yesterday. Sigma equals force over area. Remember, it is always best to draw the free body diagram, because even on this simple one, you know, a lot of people, their intuition is going to say that the force is 3,000 pounds, 3 kips. And that's not the case. When we cut this guy apart and look inside here, I only have this 1.5 kips applied to the left. So the inside only has 1.5 kips. So the internal force is 1,500 pounds. It's not the 3,000 that your intuition wants to make you think it is. So we can say sigma is 1,500 pounds. The area, I said that it had a 0.25 inch diameter, so that's pi 0.25 inches squared over 4. And we can calculate our stress. So let's see what that is. 0.2 squared times pi divided by 4. 1,500 divided by that answer is a pretty big number. 47,746.5. The units would be pounds per inch squared. That's PSI. Or 47.7 KSI. So for our structural steel, that's kind of bad. That means we yielded it. We did not fracture it, but we did yield it. So we're somewhere, we're somewhere right in here. Whoops, don't want that. Somewhere in here between fracturing and yielding. So we have permanently changed its length. Maybe we didn't want to do that, but that's what we did. All right. How do I get strain from this? So technically, I'm going to have a little bit of an issue getting strain from here because I'm going to use this equation. I'm going to use Hooke's law. Except that Hooke's law is a linear equation which really only works up to that point. Beyond that point where I'm currently at with this rod, it really is nonlinear, so it's not going to give me exactly the right amount of strain. It's going to predict something over here, right? So that amount of strain right here-ish versus being somewhere over here. So it's not going to give me the exact correct strain because I've yielded this material. But let's calculate it anyway, just to show how we could do it if it hadn't yielded. Maybe this is a stronger material. I'm sure we can find, look at that, 0.2% hardened steel has a yield strength of 62 KSI. So we would be okay with that material. So sigma equals E times epsilon. E is the modulus of elasticity for our material. For the structural steel, the modulus of elasticity is 29,000 KSI. So 29 million PSI. And our sigma that we calculated was 47,746.5 pounds per inch squared. These units will cancel each other out. So all I need to do is take 47, that number, divide by 29 million. And I get that epsilon, the strain, equals 1.65 times 10 to the negative third. And there are no units because it's PSI divided by PSI in this equation. You might write that in decimal form, or you might write it in percent form. And all of them are equivalent. They're all correct, whichever one that you prefer. Generally, the strain is going to be a small number. You don't typically have a large amount of strain because most of the time, if you're designing a machine or a building or something, maybe buildings can have more strain. But a lot of times you don't want a lot of strain because strain means that the things that you designed are not the original length that you designed them as. They have strained to some new length, and that could create all sorts of problems in your design. So typically strain is going to be a small number. Now in this case, do remember that just because we were able to calculate this number does not actually make it right, because if this was structural steel, we actually exceeded its yield strength, and now we're predicting a strain that's actually under the strain that really happened, because we entered the plastic region and the strain should have been much larger than what we predicted using this linear equation. So you do have to be careful. Just because you can write the equation for things doesn't actually make that equation right. So in this case, this would actually under predict the strain. Okay. The other thing we could have done is if we had the change in length and the original length, we could have just divided those, and that would give us the strain also. A lot of times you may have that. It just depends on what data you have. All right, let's talk about the shear strain. I'm noticing the error pop up that we might have a limited amount of bandwidth right now. I think, are we okay now? I can't tell. I think we are okay. It still gives me an error that it's not sure we're receiving enough bandwidth to actually proceed or not. But I think we are. I think maybe the camera is not working as well, which is okay. That's not the end of the world if that's not working. But I'm not sure that the actual screen. I think it is. I think it's working. It's hard for me to tell on my end. I'm gonna see if I can make the camera reactivate. All right. We'll carry on. All right, shear strain. Shear strain is similar to the idea. Remember, the difference between axial stress and shear stress was the axial stress, sometimes we call that normal stress, meant that the force that was creating the stress was perpendicular or normal to the surface area that it was acting on. And shear stress was the force that was creating the shear stress was, in our case, actually parallel to the surface it was acting on. So strain has a corollary type thing. So here, you know, we're stretching out the structural steel rod, and the forces that are causing the strain are, I guess, they're parallel to the direction of stretching, but the cross section that they're acting on is, you know, they're perpendicular to that cross section. Whereas with shear strain, I wanted to show an example like this. So this is the ground, and it doesn't move. And on the ground, we are going to put some kind of block. Let's think of it as a relatively soft block, so it's easy to change shape. And then let's say that we've glued it down here. So the bottom can't move. Now if I put a shear force across the top of this block, so I've got a shear force on top of it. Remember, the shear forces only have a single arrowhead. That's just how you can tell when you're indicating a shear force versus an axial force. The axial force has the double arrowhead, and the shear force has only half of an arrowhead, so just one triangle on top of it, or on bottom, whichever side. If this block is soft enough and I push hard enough and it's bolted or welded or glued down to the floor, then it's going to change shape and look something like this. Something like that, right? So it has skewed over. The amount of skew right here is shear strain. So all we need to do is calculate that angle. And so this angle, the amount that the part has skewed, is shear strain. Axial strain is related to how much things have stretched or compressed. We didn't do a compression one, but it would work the same way. Just the original length would be longer than the final length. So here, nothing's really changing length necessarily. Now, I probably drew it in a way that makes it look like it changed length, but it should have dropped down. I'm idealizing these pictures here, so I'm not being super accurate with all of the lengths of everything. But nothing's really changing length. You're changing an angle. So this shear strain is measured by a change in angle. So here, you just create a little triangle right here, and it has a hypotenuse. Well, we don't need the hypotenuse. It has a height and a amount of skew. So it has how far did you move that corner over, and it has how high was it to begin with. We'll just call that L. We can call that L naught, just so we have an original length, I guess. And so to calculate that angle, tangent, well, let's write that in black. Tangent of our angle gamma equals the opposite side, delta, over the adjacent side, which I called L or L naught or whatever you want to call it. And so therefore, we could solve for gamma. Gamma equals the inverse tangent of delta over that side length. Now, gamma is going to be measured in radians. And whenever you have really small angles measured in radians and you take the tangent of that small angle, it's the same number. So we often say that gamma is pretty much equal to just delta over L. Now, if you do have a large amount of shear, then calculating the actual tangent is probably better. We're also making other assumptions that, this line right here maintains a straight line and it's not curved anyway, which it probably would be. So we're making a lot of little assumptions. Probably the biggest assumption is that in general the shear strain is not large, because for the same reason that in general the axial strain is not large. You don't want all these parts of your machines and everything really changing their angles and their dimensions very much. So these need to stay small angles and small deltas. And in that case, you're probably okay with these approximations where you just take the delta over the L naught, or the size of length of that side, and that's probably close enough to the shear strain. I have a problem here somewhere. I think I put it here that will work kind of as an example for this. So why don't we copy this and paste it over here so we can work on it. So here, these little pink pieces are rubber mounts. So these, being rubber, might actually have a little more flex to them than something like a steel or whatever. And in this case, they're a vibration isolation type mount. So they are intended to actually change shape a little bit because they're absorbing this energy from whatever's vibrating this bracket. So in this case, I cut off the length here. I think that's 0.3 inches, yeah. So 0.3 inches. I just chopped it off a little bit. What it's asking us, these rubber mounts, the two pink blocks, are used to isolate the vibrational motion of whatever this little yoke is connected to. It has dimensions of L, so L down here, 0.3 inches. In W, 2 inches. And into the page, so kind of that direction, is 3.5 inches. Determine the average shear strain. Again, there's that word average. All of the things that we're doing for most of the quarter until we get to the very end are these average stresses, average strains. So we're making a little assumptions here and there. Kind of like I made with this side not being curved when it deflects over, and we're not considering the fact that when you apply a point load to something, the stress is really higher where that point load is applied, and then it averages out. So we're ignoring all of those things. So determine the average shear strain or change in angle in the rubber mounts if the rigid frame, so the gray part, the little yoke, displaces 0.011 inches vertically. So what this means is, let's just draw something that kind of looks like it. So here is our rubber block. It is somehow rigidly mounted to this wall. We're only going to draw half of it. The other half does the exact same thing, we're going to assume, so let's only draw one side. We have this frame of some sort that is mounted, glued, I guess, to the rubber pad, and this frame can move up and down and skew the pad. So this is the initial condition, and then let's copy it and just put it beside it. And then let's say that what it does is it's going to go in and skew the rubber pad. So I don't know which way we're going to make it move. It doesn't say that. It just says it moves vertically. So let's say it moves, the silver part moves up. So it's going to do something like that. And the distance from, well, hold on. Let's line it up. There, something like that. The distance from where it originally started to where it currently is, they tell us is 0.011 inches. Okay, and they also told us that this dimension is 0.3 inches. So those two, if I kind of flip this over and backwards, it's going to look a lot like this. And so what we need to do, the angle that we want is, wow, this angle here. No, that's not a gamma. That's a little more like a gamma. So we want to calculate that angle. So gamma, or shear strain, equals the 0.011 inches over the 0.3 inches. And this approximation we can just do this way. Let's do both of them so that we see if there are any different. So 0.011 divided by 0.3 gives us 0.037. No units, is inches divided by inches. If I take the inverse, well, if I switch to degree mode, which I don't remember how to do on this calculator all of a sudden. Let's see. Well, I may have to skip out on calculating this in as a tangent because I don't remember how to switch this calculator to degree modes. I don't want to spend a bunch of time trying to figure it out. I don't see it right on top of anything. Alright, well, if I were to calculate the same thing but with the actual equation, inverse tangent delta over L naught, where these I'm in degree mode, then I would essentially get the same number, 0.037. And so that's how shear strain works. It is a change in angle somewhere. Now, the last thing I think we do have time to do, the last thing I want to do is sort of related to this. And I want to calculate, if I know the force and the material and its dimensions, I want to be able to calculate how much something changes in length. So we're going to call that axial deformation. So I want to calculate a change in length. Oh, let's see. Oh, the camera hasn't been working. Yeah, I don't know what happened to, but the audio and document camera. Okay, so you can't see me, or I'm frozen in some position. That's okay. Not sure why it's that, because it actually shows it's moving on mine. But at least it's you can hear those words and you can see me writing, so that's fine. It was doing similar things yesterday on a different camera, so I don't know what exactly is going on. It might just be bandwidth issues. I'm not sure. Oh, it's working now. All right. Thank you. All right. Axial deformation, and then we'll be done for the day. So we want to calculate the change in length. Actually, we'll be done for the week, won't we? That reminds me, before I get too far, there are a couple of things that you need to be aware of. We're not too far away from a exam. So let me go back to our title page here before I forget this. So some of the upcoming things. We have quiz 1. The way this will work is it just happens in Moodle. I'll open it up. I'll usually leave it open for a couple of days, where you just pick a time that you have a time slot for about 30 minutes and do quiz 1. The way these quizzes, the ones that are labeled quiz 1 through 5, the way they work are they're the simpler concepts, the simpler problems. And so what I would do with them is treat them like an exam, where you don't do notes or anything. You have your calculator and just try to solve the problems. They count 2% each. Uh-oh, you did not get the same answer. Wow. All right. I'll have to check on that. Hopefully it was close. So these quizzes are meant to be kind of practice for the exams, but you still want to do a decent job on them. So if you can't solve one, feel free to open up a set of notes or whatever, MathCat or whatever, and get the answers that look correct. But I would try them as if I were doing test problems, because what it will do is it will give you a sense of, if you can do the quiz problems, you should be able to do the about 50-ish% of the exam problems. So about 50% of the exam is the one-step problems, the straightforward stuff. They're the easier problems. So I would do the quizzes that way. Quiz 1 won't open till Monday, but I'm just telling you ahead of time because we got several things coming up. And we'll actually have quiz 2 before exam 1. So exam 1 is not that far, but if you go click on exam 1, then there are folders with practice problems in there. So old test problems, things like that. That's the last year's exam outline. I guess you could look at that. It'll be similar. So don't wait too long to start practicing for the exams. And so now that you know a couple of the beginning topics, the stress and a little bit of strain, we'll do axial deformation in a minute. It would be probably good to go ahead and start practicing those problems. Also remember, in the web work, you have the optional problems, OP01. Those are just, 20 or 30 different problems that are of the simpler, maybe medium level type problems from the exam. And so they're good practice problems. You don't get extra credit for those. You have the challenging ones, which are the hard problems from the exam. Maybe there's only 1 or 2 hard problems on the exam. But you do have those to practice on, and those do give you extra credit if you actually get them right. So let's see. Let's go back before we get into axial deformation. Let's see about this in MathCAD. So it should have been that these numbers are more or less the same. So let's say if we do what were our dimensions? 0.011 and 0.3. I guess I should check if I even got the problem right. .037. I get both of them being .037. So maybe you didn't get it converted over to radian mode or something. Maybe it's still mixing some degree mode. Because it'll do that if MathCAD here is set to automatically do radians, and it'd be .037. If you got 2.1, then it's actually giving you degrees. So that could be what happened is if you got 2.1 when you got these two different things, then the 2.1 is probably degrees and you need to convert that to radians. But in radians, I get, if I do the inverse tangent or the arc tangent of the same numbers, I get .037. If I just divide the numbers, I get .037. So I think it might be a radian versus degree issue why you would get different numbers. The other thing that could cause them to be different numbers is if this strain was really large. So at some point, the if this wow, that's weird. This 0.011 number is pretty large. I don't know how much, 0.1 maybe. Then this approximation won't work anymore. All right, axial deformation. Oh, and I think I've noticed that the chat is several seconds behind. So if I don't answer your thing right away, it's because I haven't seen it yet. Because it seems to be like I'll write something on my screen and then it's several seconds before anybody comments on it. So I think that the chat is a couple of seconds behind. Not terribly long, but it is noticeably long. All right. Calculate the change in length. Axial deformation. So this is where we're going to combine a couple of things that we know. We're going to combine the idea of Hooke's law. We're going to combine the idea of strain, which is change in length. And we're going to combine the idea of stress, which is how the force is doing something to the object. So let's do our simple, well actually let's write those equations first. So our stress equation, sigma equals force over area. So this is the axial stress, which we define to be the intensity of internal forces. And then we had epsilon equals delta over original length. This is axial strain, and that's the severity of deformation. So how much it deformed or stretched or compressed. And then we had sigma equals E times epsilon. This is Hooke's law. And it's really only good in the linear region, the elastic region. So you do have to keep that in mind. And if you notice these equations, they all kind of have similar variables in them. So what I want to do is I want to take Hooke's law and I'm going to sub in sigma is F over A and epsilon is delta over L naught. And if I'm looking for a way to calculate axial deformation, this delta is axial deformation. So I'm just going to solve for delta. So delta equals FL over AE. And so it kind of spells flea, sort of. I guess if I did EA, it would spell flea better. But let's do it that way. For some reason, I always do AE. There we go. Now it looks more like flea. And this delta is made up of things that I generally know. I generally know how much force is applied to the component I'm working on. I should know its length if I'm designing this component or whatever. E is the modulus of elasticity, so I should know the material it's made of. And then A is a geometric property of the piece, the component. So I should know all of these things. So assuming I do know them all, I can calculate how much it will probably change in length, with a couple of exceptions. First of all, it has to be in the elastic region. So if I load it up to the point that it exits the elastic region, goes into a plastic deformation state, then this equation starts to break down, right? And we are making assumptions here that things have uniform cross sections. You know, in the real world, parts are not just rectangular, their whole cross section, and they're not just a rod for their whole cross section. So we are kind of ignoring some of the changes in the cross section. We're sort of going to take that into account in a minute, but for this equation to work, for this axial deformation equation to work, I do need to have all of these constants. So I need a constant force on a constant material, on a constant cross-sectional area, and I need to know the length of that area where all of this is constant. If it is not constant, then I'm going to have to break it up into little pieces where all of these values are constant and do them one at a time. And we'll do that in a second so you can see what I mean. All right, let's start with the super simple. Let's use a rectangle this time because we've been using these round rods and I feel like the rectangles are getting left out. So here we've got a rectangle and we're going to put an axial force here and a reaction to it over here. Let's say that this force is 2,000 pounds. And the reaction needs to also be 2,000 pounds. I'm not going to put a hole in this one because that would change this cross section, and then I would not have a constant cross section in my equation, so I don't want that. Let's see, what I do want is some dimensions on here. Let's make this 1, 2, 3, 4, 5, 6, 7 inches long. Let's make it not 1 inch thick because I want it to actually have a chance of, you know, being relatively thin. Let's make it a 1/4 inch thick. And let's make it, I don't have a good place to put this dimension. Make it 2 inches this way. All right, and let's make it out of our structural steel. Okay. What we need now is to solve for this change in length. So what this does, again, it's ignoring the fact that at this point load right here, I probably have a concentrated force where it would pull out just that little section. You know, I'm ignoring all of those kind of things, and we're just thinking of average change in length. So if I use my equation, delta equals FL over EA. Again, it is better. You know, it seems a little bit silly when there's just one piece, but it's better to cut the thing open, draw the free body diagram of one piece. I'm going to draw this side. And determine what the internal force is, so that you don't fall into the accidental trap of thinking there's 4,000 pounds on this when there's really only 2,000 pounds inside it. So this is our little cross, you know, the cross section in the middle. So delta is equal to the F here is the internal force, the one that we just drew. It can be positive or negative. Remember, we're going to assume that tensile forces are positive. Whoops, my keyboard's kind of getting in the way here. So we're assuming tension equals positive and compression is a negative force or strain or whatever. So this arrow that I just drew, this one here, is pointing away from the body, which makes it a tensile arrow. So I have a positive 2,000 pounds. The length here, sometimes some people get confused. I tell them to cut the body apart in the middle, and so they think the length is half of it, but what the length is the length of the entire body that I'm modeling. So here, I'm modeling this whole 7-inch by quarter-inch plate. The length is 7 inches. So the length of the whole plate, not the length of the free body diagram. The length of where F, E, and A are all constant. E, structural steel, I don't know if you remember, but you go back to your chart, and the structural steel is 29 million psi. A is the cross-sectional area, the little red shaded area, which is 2 inches by 0.25 inches. I know all of those values, so I should be able to put them in my calculator and calculate the change in length of this bar. So we have 29 million times 2 times 0.25, 2,000 times 7, and then divided by that denominator is, small number, 9.66. These units would be inches. You can go through and see how the pounds canceled out with the pounds per square inch. The square inches from the area cancels out with the square inches in the bottom of the denominator of the modulus of elasticity, and that leaves the inches from the 7. So this is inches, and wait, it's not 9.6 inches, it's 9.66 times 10 to the negative fourth. And typically these are going to be small displacements because, again, you don't really want the parts of your machines and all change in length that much. So that should be pretty straightforward. Let's take one level higher. And it's not that it's more complicated, but we just have to be a little more careful. So now let's do one hanging from a ceiling just so that it's a different orientation. Okay, so there's our ceiling, and we're going to have some sort of piece here, and then attached to that one, it's going to be a little bit smaller piece. And so let's go back to these being round. So this is a round cylinder with a thinner round cylinder hanging from it, or attached to it beneath it. Let's put some dimensions on here. This one will be actually let's make it big, 48 inches. Let's make this one, even though it looks the same on my drawing here, let's make it 60 inches so that we can track the numbers better in the equations. Let's give this guy a 0.75 inch diameter, and let's give this one a 0.25 inch diameter. Let's make the thinner one from the structural steel, and let's make the other one from a different material. Let's see what other materials. Oh, did I close them all? I think they're maybe still open. There they are. So that one's structural steel. Let's use this cast aluminum 195 T6. Let's use that for the bigger one. So 195 T6 aluminum. Okay, and we need some forces. Let's put a large force here, pulling down on the structural steel part, and let's say that that is 5 kips. Oh well, that's a thinner piece. Let's actually not make it quite that much. Let's make it 2 kips. And then here, I've got some kind of collar or something that is evenly pressing upwards on the aluminum piece. Let's make that one 5 kips. So there's some piece that's not shown, maybe some kind of ring or whatever that's around the structural steel piece, and it's pushing up on the aluminum piece, if that makes sense. And I've connected all of these arrows together kind of to show that it's evenly spaced. This 5,000 pounds is evenly spaced around the aluminum part. It's not 4 5,000 pound loads just because I drew 4 arrows. When I connect all the arrows together, that means that it's just distributed around. If I did not connect them, if I didn't draw the line that connects them together, then yeah, that'd be 4 5,000 pound loads. But when I connect them together, I mean that they're just distributed out around the thing. All right. So what I need to do with this is I want to solve my equation delta equals FL over EA, but I have different things here. I have different regions that have different forces, I have different materials, and I have different cross-sectional areas. So what I'm going to do is I'm going to define, in this case, 2 distinct regions. One region that is the structural steel rod, because it will have the same force, the same material, structural steel, and the same cross-sectional area, so that can be one region. And then the other region will be the aluminum piece, where it'll have a force that's constant in the aluminum piece. It'll have a constant modulus of elasticity because it's all aluminum. And it'll have a constant cross-section because it is drawn as a 0.75 inch diameter cylinder. So I have to do 2 different regions. So here, I'm going to start at the bottom, and I'm going to draw my free body diagram of region 1, the structural steel. So I've drawn my little green line where I'm going to cut it open. I'll draw that free body right here. And it has 2 kips here, and that's all the force that's applied to it. So the internal force needs to also be 2 kips, and that arrow goes away from the free body I drew, so it's a tension. It's trying to pull this longer. This is a reason why you draw the free body diagrams in the center of the regions, because if you drew it here, then it gets confusing on what to do with the 5 kips. You know, do you put it on? Is it on the other side of the green line that I drew, or is it, you know, do I half it up? What do it do? I don't know. But if you draw the free body diagram through the center of the region, then it's pretty obvious that, well, I don't even need the 5 kips on this free body diagram because I've clearly cut it off of there. So here, I could solve this one. We could call this delta 1 equals, there's 2,000 pounds. It's a tensile load, so it's a positive 2,000 pounds. This has a length of 60 inches for region 1. This is all of the structural steel. So the length has to define the length of the region, and the region has to have a constant force, modulus of elasticity, and cross-sectional area. And so all of the structural steel falls into that category. So I use the 60 inches as the length here. We can still use our 29 million psi for the modulus of elasticity of structural steel. And then it has a cross-sectional area. It has a diameter, so pi times 0.25 inches squared over 4. So we should be able to calculate this guy. The equation's getting a little bit more complicated, but I think we can do it. 0.25 squared times pi divided by 4 times 29 million. I think I got all that in there. 20, or whoops, I didn't. All right, let me start over. 0.25. 0.25 squared times pi divided by 4 times 29 million. 2,000 times 60 divided by the denominator. All right, so we get a little bit more than we got last time. 0 is positive, so it means it got longer. It's intention. 0.08, and I'll call it 4. Our units will be inches. And that's just for the structural steel. So that's just from, well, the length of the structural steel got longer by 0.084 inches. Now we need to see what is happening to the aluminum section. So I drew a new, this is section 1, or region 1, that's region 2. I drew a new free body diagram, or I'm about to draw a new free body diagram. I have to include region 1 in this because of I drew the little line here at line 2, the green wavy line at line 2. And if I could draw the top half, you know, just this little piece on top, but it's connected to the ceiling, and I don't want the ceiling there because I want a free body diagram, so I don't want it connected to the ceiling. So I'm going to draw the other half, which is here, the green line all the way down the rest of the body. So I do have to include region 1 in this. We have the 2 kips sliding around on me. We have the 2 kips here. I have the 5 kips spread out here. So for this body to be in equilibrium, the free body I just drew, for it to be in equilibrium, I have 5,000 pounds pointing upwards, 2,000 pounds pointing downwards. I need another 3,000 pounds pointing down. That's going to be a little confusing with those two right next to each other. Let's do that. So the internal force here in section 2, so for delta 2, is pointing towards the body. So that's a negative, that's a compression, negative 3,000 pounds. The length of just section 2, not the free body diagram, but the length of section 2 is 48 inches. The modulus of elasticity of section 2, it's that 195 T6 aluminum. I don't know that one offhand. Let's find it out. 10.3 thousand KSI. So 10.3 million PSI. Or, yeah, 10.3 million PSI. So 10.3 times 10 to the 6th PSI for the modulus of elasticity. And then its cross-sectional area, it has a larger diameter. So pi d, which is 3/4 of an inch, squared over 4. And I will get, let's calculate that number, 0.75 squared times pi divided by 4 times 10,300,000. 3,000 times 48 divided by the denominator is negative, so this one is getting shorter, negative 0.032 inches. So the total change in length from top to bottom of our composite fixture here, delta total, is delta 1 plus delta 2 is 0.084 inches minus 0.032 inches equals 0.084 minus or plus negative 0.032 So overall, the point at the very bottom, overall point A does move down, but it doesn't move down by the total amount that section 1 stretched. Section 1 actually stretched 84 thousandths, but point A only moved down 52 thousandths because section 2, the aluminum piece, actually got shorter by 32 thousandths. So I think we're about out of time. I have opened up some web work problems to let you practice on this change in length, axial deformation. There is one problem in there that's a little annoying, and it's one of these, and it has you kind of try to estimate the modulus of elasticity, and it's very picky. So if you get into the web work and you just can't get the modulus of elasticity to come out right, just send me an email from WebWork and I'll let you know what it's expecting. And it's only because you're reading off of a graph and trying to read the exact same numbers that the whoever coded that problem read, and it's a little bit tricky to get those numbers the same all the time. So if you have problems on that particular one, let me know and I will show you what numbers it's expecting for you. All right, I will be back Monday for this, and what will we do? We'll be doing not that. We'll start on our idea of some trusses, and we'll start dealing with those moments. And we haven't done that yet. We've only done forces in X, Y, and even Z directions, but now we'll be able to do some moments also. All right, I will see you guys on Monday. If you have any questions, let me know, and we will come back. Hopefully I can get my streams to be a little more stable. I don't know exactly what's going on with the cameras on it though, but they kind of keep flicking out a little bit. All right, see you Monday.